Alright, in this video we're going to go through that graphing assignment, make a little answer key. I'm going to go through fairly quickly. Looking at it from the transformations perspective, we see we go right 5 and down 3. But also realizing that because there's a -2 there, it's a horizontal compression, and it's been reflected. So it would have looked something like that, would have gone in that direction. And what we want to do is find the x-intercept, set y to 0, and solve. Rearrange that equation a little bit, you find that x equals 1/2. So there's our point. And so basically what's happening is take that shape, but we move it 5 to the right and down 3 to that vertex that we know is there. We could find the y-intercept as well. We see it's √10 minus 3, which is a little bit more than 0, around 0.1. There's our graph, and we know the domains, everything less than or equal to 5. The range is everything above -3. Alright, next up, might as well move the 5 to the other side. You can see that there's a vertex at -4, 5, and also that would have been the shape just based on the reflection and the vertical compression of 2, something along those lines. But we know we actually have to start at -4, 5. So again, you can find the y-intercept by making x 0. You find that it's 1. And then you find the x-intercept by making y 0. A little bit more. You square both sides. And you see, let's grab a calculator for that one if you want. It's around 2.25. You can do that by hand as well. But we know it looks something along those lines. And the domain, x is greater than or equal to -4, y is less than or equal to 5 for the range. Alright, now we're into a rational function. So we can see there's definitely going to be vertical asymptotes at 3 and -3, and a horizontal asymptote at 0 because the bottom degree is bigger than the top. After that, you can find the y-intercept by plugging in 0 for x. You find that it's also 0. This is one of those cases where you actually have a point on the horizontal asymptote, and that's okay. After that, we can check a few points, plug them in, 1, and then so on, go through and evaluate for y. And you can figure out that it's 1/8. Turns out to be positive. You can try 2. It's 2/5 and so on. Eventually you start to realize that it's making a shape that looks something like that, and you can check on the other side of the y-axis, and it basically mirrors itself with the negative versions of it. There's an example with -2 for x. So it looks something like that between the two asymptotes. And then on the outside of the asymptotes, again, you could try a number like, say, x equals 4. You plug it in, you end up with a negative when you're on the right side. When you plug in -4, you end up with a positive. And there's our graph. Now the domain is everything except for the asymptotes, and the range is actually everything because we actually do have a point at 0. Alright, this is one where the degrees are the same. So we look at the ratio for the horizontal asymptote, the ratio of leading coefficients. Vertical asymptote we just found from setting the denominator to 0. And once again, we will find the y-intercept, make x 0, you end up with 4/7. And there's our x-intercept. Turns out to be 1/2. So we have a little arm in the kind of top left quadrant. And again, you can check a point at, say, x equals 3. Find out where that is, and fill in our graph accordingly. Alright, so when in doubt, make a little table of values and check your points. Alright, this was the trickiest question. So first thing you want to do is factor the top and the bottom, because usually when you have trinomials like this, something will end up canceling out. And so in this case, it's the x minus 3 that cancels out, which means we have a hole at x equals 3. Now vertical asymptote, same rule as before, it's just -5. And this time the top degree is bigger than the bottom, which means there's no horizontal asymptote. What there is there's a slant asymptote, and you can find it by using division. Whoops, there you go, fix that up. In this case, I'll use synthetic division. You get left with 1 minus 1, so that represents y equals x minus 1. The remainder, not really important at this moment. We know at least that we've got a slant asymptote at y equals x minus 1. And then it's a matter of figuring out your intercepts and figuring out roughly where that graph belongs. So we know 0, 0 is a point. And it depends how accurate you want to get, how many points you want to find, but it does something along those lines. It's trapped between the vertical and the slant asymptote. And then I just tried some numbers over on the left side of the asymptote. So I started with -8 and put me down around -10.6, somewhere down there. And I did realize later that once I started to do the range, that point's probably a little bit too high. The range is kind of tricky to do. We know it's everything above the bottom of that top part, and it's everything below the top of that bottom sort of curve. Now, it's tricky to find actually without a calculator or without some calculus skills. So I did use a calculator to check this, and I realized that my function should have been a little lower. It's everything below about -10.47. Alright, so hopefully you found that helpful. You can go through those 5 graphs, make sure you can do all of those types. Lastly, just looking at the 3 sort of different things that can happen with horizontal asymptotes. Remember, it always comes from comparing the degrees of the numerator and denominator. So in this exercise, you saw one of each type. If the bottom is bigger than the top, you have a horizontal asymptote at y = 0. If they're the same degree, it's the ratio of the coefficients. And if the top's bigger than the bottom, you usually end up with a slant asymptote. At least there's no horizontal. And remember, in the first case, you can always transform it. You could have moved it up or down from 0. And basically, where these things come from, it is calculus, but you can basically plug in large x values as well and just figure out where is y getting closer and closer to as you plug in bigger x's. Right? It's called something limits at infinity in calculus terms. Alright, thanks for watching. Hope you enjoyed.